Hi, this is Mrs. Villette, and I'm here to finish example 2 from your section 4.2 notes. What we had talked about so far in this example was finding the domain, and that was setting the denominator not equal to 0. We factored the function completely. We had already factored the denominator in step A, so we just factored the numerator. The vertical asymptote, which came from the zeros of the denominator, so -6 and +1. The x-intercept, which came from the 0 of the numerator, the y-intercept, which came from setting x to 0. From that, we were able to create a very limited portion of the graph. We could create the vertical asymptotes at -6 and 1. We could create the x-intercept and the y-intercept. I want to explain a little bit more about how I know what's going on in this middle portion. So at the x-intercept, there was actually an x plus 1 squared in our function if you look at your notes, and that means that the function bounces off the x-intercept. We also had the y-intercept right here at -1/3. In order to connect those two smoothly, I automatically knew I had to go down toward this I had to go down toward this vertical asymptote. Now, because I had no other x-intercepts and I knew I bounced at 1, then I had to be going down this other way. This middle part is not actually a parabola. It just behaves at the 0 like a parabola in that it bounces. Now I want you to notice I don't have anything over here to the right of 1 and to the left of -6. So our job now is to create either a sign chart or a table of values in order to figure out what happens there. So I'm going to use this space down here to create a table of values, and I'm going to use the factored form of my function. So 2 times x plus 1 squared over x subtract 1 x plus 6. And I'm just going to try to create some values on either side of the asymptotes and the x-intercepts. So I know that there's an asymptote at -6. I'm going to plug in something pretty far to the left of -6, which is -10. So that's going to look like 2 times -10 plus 1 squared over -10 subtract 1, -10 plus 6. So 2 times -9 squared over -11 times -4. Notice that I'm just working down each piece. The denominator is 44, and the numerator is 2 times 81, which is 162. This is about 4. It's not 4. You can go ahead and divide in your calculator. We're just trying to get an idea, so I'll go ahead and actually divide. It's 3.68 is what that number is. So I can go ahead and place that point on the graph. Okay, so we keep going with this, and let's plug in something closer to the x-intercept. The x-intercept was -6, so let's plug in -7. I'm going to show fewer steps. I'm going to plug in here in my head. So -7 plus 1 is -6 squared. This is going to be -8 times -1. So 2 times 36, which is 72 over 8. 72 divided by 8 is 9. Okay, and we already know what happens in between, but just to be sure, we'll plug in -5. So -5 plus 1 is -4. And then I have -6 and +1. So 2 times 16 is 32 over -6. And I'm using my calculator just to do this division here. I get -5.3, about there. Which is pretty consistent with what I drew. Not perfect, but it's pretty close. And if we didn't know what was happening, I could continue to evaluate more values, but I want you to notice that I do have that portion of my graph already filled in. So I'll put some things that are to the right of 1. So to the right of 1, I'll put in 2. So 2 times 3 squared over 2 minus 1, which is 1, and then times 8. So 2 multiplied by 9 is 18 over 8. Or that is the same thing as 9/4 or 2.25. And then just to get something further away, let's plug in 10. So 2 times 11 squared over 10 multiplied by 16. So 121 doubled is 242 over 160. So it's about 1.512. Okay, let's get some more points on there. We'll get all our points. So -7, +9 is right there. And then we have -5, -5.3, which we were actually fairly close right there. 2, 2.25. It's about like that. And then 10, 1.512. Now, this doesn't give us a perfect idea of what happens, but we do see that in order to be a rational function, it's going to have to get close to those vertical asymptotes. If we want to figure out what happens with the horizontal asymptotes, we need to go even further. I'll use this space up here. So to find the horizontal asymptotes, we need to be thinking about x going to infinity. Now I can't actually reach infinity, so let's try a bigger number, like x equals 100. So f at 100 is 2 times 101 squared over 100 times 106. I'm going to use my calculator for this. So I get 20,402 over 10,600. And if I divide, I get about 1.92. A horizontal asymptote is only one number for a rational function, so I don't need to go the other way. Let's try bigger. Let's try 1,000. Actually, let's go even bigger. Let's try 10,000. So f of 10,000. We're doing 2 times 10,001 squared over, oops, this other one should have been 999. That will change our number, not 99, 99. That will change our answer just by a little bit. I'll fix that in a minute. 9,999 multiplied by 10,006. Okay, so here we're getting a really, really, really big number. And then also a fairly big number. Now, if you just pay attention to what's going on at the beginning of these numbers, though, it looks like it's about a 2-to-1 ratio. I have big numbers. I've got, some other decimal places other than zeros, not decimal places, but place values here other than 0. But basically this ratio looks like it's tending toward 2. So if I plug this in, I get 1.999, which is pretty darn close to 2. The asymptote is as x goes to infinity, so the further and further I go, the closer and closer I'm going to get to 2. So I'm not really worried about this answer being wrong so much. I'll go ahead and fix it though. So the bottom number should have been 10,494. And so 1.94 instead of 1.92. Nope, I don't know why it's not erasing for me. Okay, we'll just say that. So it looks like the horizontal asymptote is 2. What does that mean for our graph? Well, let's take a look. We had some points on our graph. In fact, we had this point down here that was below 2. We're going to go ahead and put our horizontal asymptote on the graph. So my function does cross below my horizontal asymptote. I can see that. So at some point it has to dip down and then it needs to come back up, because the definition of a horizontal asymptote is a horizontal line that the function gets close to as x gets closer to infinity. This other piece, I don't think it actually dips below. We could get more table numbers in our table of value to figure that out, but I'm going to go ahead and say it looks like that, and then I'm just going to check in Desmos. So a lot of this is sort of your best educated guess. There is a strategy to tell if they cross the asymptotes, but we haven't talked about that yet. So overall, what we did in this problem was we found the domain, we found the vertical asymptotes, the x-intercepts, the y-intercept. We used a table of values to try to figure out the rest of the behavior. And then we found the horizontal asymptote by letting x get successively larger and larger and larger. What we want to look at next is how to find the horizontal asymptotes using some algebraic technique. So later on in the notes, you'll see something about horizontal asymptotes. And this is something you can do on your own. It's actually a very good exploration. You will need a calculator. And what you're going to do is try to figure out what the horizontal asymptote is by just plugging in larger and larger values for x. And actually this last table should have one more 0 in it, so go ahead and add that on. So each one of these should have another 0. And really what we want to pay attention to what's happening is what's happening to those numbers, what are they getting close to, but then what's the final number down here, and if we can guess at what that ratio will be, if it does in fact appear to be approaching a single number. So you can see the first example I plugged in 10. 3 times 10 is 30, plus 1 is 31. 2 times 10 is 20, minus 1 is 19. Evaluate the numerator and denominator separately and then divide, and we got about 1.63. You're going to do that for each one and then try to determine the asymptote. The rest of the notes, you can work through those on your own and look at the completed notes in Moodle for a guide.